Hello, folks. This is Answer Everywhere. We're taking a look at the source code for R, the statistics software. I know a lot of data scientists, including myself when I do data science, are focused on Python, and Python has a number of really great data sciencey libraries like NumPy and Pandas that allow you to have like an array driven workflow. And those are really good. But I think that R is a really underappreciated language in data science. It has a more natural kind of fundamental array-driven workflow, and it has a bunch of statistical utilities built in that are a little bit easier to access to work quickly with. So I thought it would be fun to take a look at the R source code. If I remember correctly, it's based on a previous closed source statistics language called S, presumably S for statistics. And my mental model of R is that it's going to be something like C macros that call Fortran, optimized Fortran linear algebra libraries. It's probably not actually just macros, but they're probably, I'm going to guess there is a lot of under the hood, a highly optimized third-party linear algebra library that's doing a lot of the heavy mathematical work, which would also be, I think, how something like MATLAB is implemented. But we'll see. And then there should also be more of a statistics focus than if we were looking at data science libraries in general. Like we've looked at a lot of machine learning libraries, and machine learning uses some of the ideas from statistics, but it's less, the language itself of Python and the NumPy and Pandas libraries are kind of data in general as opposed to statistics in particular. So let's take a look. So we see that almost 40% is written in R, about 30% in C, and then somewhere between a fifth and a quarter in Fortran, as I suspected. We do get a basic R README. The core of R is an interpreted computer language with a syntax superficially similar to C, but which is actually a functional programming language, in quotes, with capabilities similar to Scheme. I've never really thought of R as being similar to Scheme, but I guess I've also never used Scheme. We do have a history section. It was originally written by Robert Gentleman and Ross Ithaca, the Hecka, of the Statistics Department of the University of Auckland. In addition, a large group of individuals has contributed to R by sending code and bug reports. Okay, and I think it was here. The present version implements most of the functionality in the 1988 book, The New S Language, the Blue Book, and many of the applications. Okay, so whatever the S language is, how about S programming language? It's a statistical program from Bell Labs, primarily by John Chambers. I don't feel like I've heard that name. I don't know if I just know him from R. To turn ideas into software quickly and faithfully. Okay, so that's the idea. John Chambers, he's a core member of the R programming language. So I guess he created S and moved to R. All right, cool. So let's look at the code. And by the way, next week is the monthly fan request. I'm probably doing, well, we'll see. But I'm doing one of the requests, possibly something JavaScripty, possibly something Linux kernel-y, but we'll find out next week. Okay, so I think everything should be in source. This is, by the way, not the official source code. This is a mirror of the official development source code, which is in Subversion. I do have a local clone of the Subversion repo, but I figured it's often easier to use the tabs of the web browser and look at it in GitHub. Okay, so we have library main modules nmath. I don't know what nmath would be. Scripts, Unix, This GNU Win32 is almost certainly some Windows compatibility layer that somehow involves GNU, possibly some sort of like port of the GNU toolkit to Windows land. Extra and Apple. Apple, I'm going to say is probably applications. So let's, definitely main and library, possibly modules, possibly Apple. And what about Nmath? We'll look at Nmath in this tab and possibly sacrifice it to the gods. Nmath looks good. We have Bessel. These are almost certainly the Bessel functions. And numerical math maybe. Beta, D beta is probably the beta distribution. D Cauchy is probably the Cauchy distribution. So this looks like stats stuff. So let's make sure we see that. But we'll look at it, I guess, after we look at the main infrastructure. We have some command line argument parsing, a random number generator, which is hopefully pretty good since we're using it for stats. How do I find out? Are they implementing their own? We have an RNG type. This struct has an RNG tab, maybe table, that has things like a seed and an RNG type. And what are these the types? Yeah, Wickman Hill, Marsaglia multi-carry, super duper. And what is Buggy Kinderman Ramage? And here, I see Mersenne Twister. What is this? This is a name. Oh, okay. So this name Mersenne Twister is just, this is like the print version of the name. Okay, so these are different RNGs. Hopefully some of them are good. I don't see the backdoored RNG. What is that, the dual something? NSA probably? The dual EC DRBG. That's one to avoid. Okay, so these are some RNGs. Alloca is probably allocators. Alloca. Allocate automatically reclaimed memory. This implementation of the PWB library alloca function, which is used to allocate free space off the runtime stack so that it is automatically reclaimed upon procedure exit. So this is basically garbage collection. All right. We're not going to look too closely at this. There should be some interesting stuff about how like arrays happen, but I'm going to guess that that's mostly in the underlying Fortran. We have connections, which is maybe internet connections. Large file support. The stdio functions, such as fseek and ftel, are defined using long for file positioning. So this is things like open files, socket connections. Okay, so this is interacting with files, possibly over the internet via sockets, possibly over the local machine using sockets. And what else do we see? Engine. Engine could be anything. A note on memory management. GE destroy dev desk. It's not GC, it's not garbage collection. I don't know what GE is. GE system state. Maybe engine, something engine, general engine. Oh, what? That shouldn't happen. Graphics engine. Okay, so this is some graphics stuff for probably like plotting. I'm going to kind of just move along. R complex. I doubt this is complex numbers. GCC has problems with header files on, for example, Solaris. Okay, so this is some stuff to help it build, I guess, on different systems. Then we have devices. This is probably like devices in the Unix sense as opposed to like computers or machines. Tstruct engine we saw as graphics engine. FlexiBLAS. BLAS is probably the BLAS linear algebra library. we've got some S expression, R flexiblast info, void. And if this is defined, have DL sim, and we have RECL rizzled default, etc., then we set FCB name to flexiblast current backend. And what is this? This is some infinite for loop. So forever, if we have a name, we're going to free it, exponentially grow the size, malloc some stuff, or rather try to malloc it. And if we don't have a name, we break. Otherwise, we copy the, I forget how string copy goes. I think it copies the prefix into the name. So source to destination, okay. We copy the prefix to the name. We try whatever FCB is. Flexiblast something maybe. And et cetera, et cetera. So I don't know really what that's doing. It's trying to set some name up and possibly failing. And then we have a bunch of Gs. Gs might be graphics, extern, font, some stuff about events. We have a grep file. Why? I don't know. This is something I'm checking for interrupts. Max stack size. This is some stuff about PCRE2 is a well-known regular expression library. Okay, so I think all of this is mostly not so interesting. I did see some stuff about LabPack, which is another. Here's some plot stuff. I guess I do kind of want to maybe see plot, but later. QSort is probably quicksort. Radix sort is probably the radix sort algorithm. I don't know what else it could be. Source, I don't know what that would be, but let's look at LabPack. I just want to make sure I'm not missing anything too fundamental to how we should think about R as I'm looking at the other stuff. All right. So we have this LA init function. We've got this R module C dynamic load. LabPack, I guess probably has an R module. Module / labpack/labpack.c. And if it's, we'll start by assuming it's not initialized. And if we don't get a result back from the load, then I don't know where PTR came from, but we'll look at the PTR do LabPack. I guess it's some Boolean or something. And if it's not populated, then we say that the routines cannot be the LabPack routines cannot be accessed in the module. Otherwise, we say that it's initialized. Again, here's some more S expression stuff, which seems to be consistent with their claim that it's kind of a Lispy inspired thing. And here's do LabPack. We're going to check arity on the arguments, which come from here. I'm not sure why, but I guess that's what we'll do. And then, or maybe arguments needs to be like a list of tuples, so they should all be even or something. And then if things are not initialized, then we'll try to initialize them, which is the function we just saw. Okay, fine. That's all relatively straightforward and boring. Then here are the libraries, and these include base, which is the kind of main, I think, entry point, a compiler. I don't know if this is compiler support for compiling R or compiling R source code. So it's a function. It's a compiler written in R, so it probably must be for R source code. You can get compiler option. These are utilities for pasting dots or missing. I don't know what the dots is. Maybe this is for looking for some ... notation, which I think is a thing in R. And then we have some things like frame types. Like I think like a data frame similar to like a pandas data frame, and so on. So this is some compiler stuff. We'll just take a quick tour here because this is going to be it's an old language, and it's like a pretty full-featured language. So we're not going to be able to see everything if we stay too long on things that are just kind of interesting, but not necessarily fundamental. Let's pull library out. Stats And I don't know the difference between stats and stats4 will be. There's tickle, TK. A grid graphics. I definitely want to look at base. What is methods? Parallel, I'm going to guess, is just support for parallel processing algorithms that run on multiple cores. Defunct methods.r, next method. Methods may be for making functions, but I'm not sure. I'm going to look at base and then stats. All right, so what's in base? We have Unix. We have the Bessel R function. We saw a reference to the Bessel C source code. Deprecated defunct S3 extensions. Scripts append. I'm guessing this is just literally appending the data frame apply. Let's look at apply. Let's look at array. As is presumably something like type conversion. Assign is probably assignment. Attach. I think attach is like puts things in the global namespace. How to use attach in R with examples. You can attach data, and then I think you get all of their columns as variables. So if you attach this data frame, I think that you now can, instead of saying like df dot, hey, stop that. Instead of saying df dot team, you can now just say team or something. I believe. Do I have R installed? I'm not sure how I can do a, let's take this. So I can do something like df.team or $team. And I can also attach df. So if I try team, nothing, but let's try attaching team. Or rather, attaching df. And now we do have team. And so I can do something like a linear model of points by rebounds. Now I get something, and I think I can plot it. Wait, what? How did reverse search fail? Let's just grab it then. And this is some plot of the linear model, although I don't know why it's working so hard. Oh, it's multiple plots, and I have to like scroll through them. Okay, so this is a very poor model. Actually, it's not so bad. Wait, no, this is quantiles. Where's the actual regression? I'm not sure. Fitted values. Okay, so there's some, you can fit a model, and you can see some of the like all of the related statistics that help you evaluate whether the model is a good one. Bitwise is almost certainly going to be like bitwise operations, like fast bitwise and stuff. But in R, because this is an R file, and it's probably just somehow calling out the C to make that happen. Chol is something. The Cholesky factorization, which I don't think the DF matrix is, but that's fine. So then we have also column sums, conditionals, etc. Cut, I forget what cut is. My mouth is getting very dry. Hey, Friction, good to see you, and thanks again for the whatever this is called. Is this a super chat? I really appreciate it. Yeah, I sometimes forget the R syntax. If you're moving back and forth, like pandas and NumPy try to be R-like. Like a lot of the stuff that works in R, like later showed up, I think, in things like IPython and the Panda data science tools. Oh wait, what is cut? So cut divides the range of X into intervals and codes the values in X according to the interval, to which interval they fall in. So you just call it on an array-like thing. So if we try, what do we have, points? If we try cut points, does that work? Oh, breaks is missing with no default. But where's the default here? Either a numeric vector of 2 or more unique cut points. Yeah, I don't know. I guess I have to supply some breaks, or maybe the points is not long enough or something. What else do I have? Assist. What if I try cutting point? What if I try to concatenate? So concatenate is C, I'm pretty sure. So concatenate points and rebounds. And what if I set breaks to just a number? There, whatever that is. I guess these are, we get two like half open intervals, 86 to 92.5 and 92.5 to 99. And we see which interval I think each point falls in, is what this is. So this falls into the first interval, this is the second, and so on. Okay, so that's for like slicing up, I think, continuous data into something more discrete so that you can use some of the discrete tools. Like sometimes you have something like you're doing something like looking at a demographic thing like height, and you want to divide it into like tall people versus short people, and you can use something like cut for that. And we also have dates, debug, diag, maybe the diagonal of a matrix. Yeah, so the first thing we do is we check if it's a matrix. All right, cool. And I saw something about LAPACK, all caps. This is single value decomposition. And what are we doing? We check if it's logical, if it's numeric, if it's complex. And this is some stuff with new and NV, NU and NV. I guess these are the maybe the parts of the number of, I don't know. Probably number of something, but I don't see an explicit call to LAPACK, which is what I was looking for. So I'm guessing that the call to LAPACK is either in this dot internal thing, LA SVT complex, or is just in matrix. Then everything else is kind of like just getting things in the right format for sending to matrix. Do we have matrix? Here's the det, which is probably determinant. We have data.matrix, data frame. I guess we'll look at data frame. And maybe we'll just move on. Traceback utils vector. I don't know really how a vector is different from an array. I'm guessing maybe vector is the more vectory thing. And then we have ZZZ, which is what? As numeric, I guess we're just aliasing. As numeric is an alias for as double. Is names is an alias for is symbol. And something about S3 generics. I don't know what this is. Assign.call function name package. This kind of looks now more a little bit like some of the macros we've seen in defining Lisp. But I don't know why this is called ZZZ. This is just kind of like metadata, setting stuff up, it looks like. So I will ignore it. Okay, so I've opened a bunch of files from there. I think I'm going to look at stats, and then we'll kind of look at all the R files together. I see some stuff here like tests, source, and R. What's the difference between source and test? So source is the C files, and R, the R directory is the R files. Should we look at optimize? Sure, why not? Random is mainly, I think, going to be called calling the RNG. We have a stats header. We should see some possibly stuff like Gaussian, normal. We have this Wishart thing, which is, I believe, a distribution. I will look at a couple of those. And then our folder, we have a bunch of things. Kalman is maybe a Kalman filter. I don't know if Kalman did anything else. Tukey, HSD. Maybe Tukey tests, maybe other things. Bandwidths might be fun. Some stuff about like binomial test, the biplot. Birthday is maybe birthday paradox. Can I send a link to the repo? Yeah, sure. This is just a whoops. This is just a mirror. This is what I'm looking at. And why is this not working? Give me a second. I'm trying to copy from the VM to the outside world, which used to work. Yeah, okay. All right. So Friedman test, interaction, plot, integrate. I guess we'll look at integrate. That's probably, like numerical integration. The Kruskal test. Yeah, no problem. Log linear, Mahalanobus, which I'm mainly aware of as a distance. It's kind of a fun name to say. Optim is probably optimize, plot. LM is probably the function I called when I called plot on the linear model. And we have things like an ANOVA test, possibly just computing the power of an ANOVA test. I guess we'll open power and power ANOVA test, predict. I don't know what predict is. Can I call predict on the linear model? Let's try it. Now backward search works. Yeah, so what am I predicting? I don't know. I have, these are just 1, 2, 3, 4, 5. Maybe if I give it a range to actually predict. I'm not sure. Okay, and then QQ plot is like the quantile plot. QQ norm is, I think, the QQ plot for normal variables or something like that. SD should be standard deviation. Splines, step fun, t-test, and some other stuff. We'll just open a few of these. X tabs. I'm using Linux, various versions of Ubuntu. Various descendants of Debian is what I meant to say. I don't know what stats 4 is, but we have BIC and MLE. MLE, something multi, no. MLE is, I'm thinking of MSE, mean square error. I don't know what, I figured out MLE is. Multilinear. I think it's something in the regression. Maximum likelihood estimation. Yeah. Okay. So this is presumably maximum likelihood estimation. We have a class, set class MLE representation. I don't know what this is, but the call is set to language. Coefficients are numeric. Full coefficients are numeric, fixed. VCOV, something maybe variance, covariance. And then this is perhaps kind of like metadata stuff. And then we have the implementation. The first argument is minus log L. Then we have start. The optim is some optimizer, stats optim. And method, if use lim, then the method is BFGS. Else it's LBFGSB. I don't know what BFGS is. Broyden-Fletcher, Goldman-Farb, Shano algorithm. It's a numerical optimizer for solving unconstrained nonlinear optimization problems. Okay, Which, that's a pretty generic set of problems, I think. All right, and then we're going to set call to match call. I don't know where match came from. And we're going to use lapply. I don't know what this log L thing is doing, and so on. But since I don't really know what stats4 means, or if this is just like I don't know if this is a generic implementation of MLE or if it's something more specific, so I'm not going to look too closely at it. But BIC is what? Probably some other, I don't know. Probably Bayesian information criterion, which leaves this as the AIC CACA something information criterion. A CACA? But again, I don't know what this is doing. It's just calling set generic on two things. So that folder is too mysterious for me. Here's base, which I thought we looked at. I'm just going to close it. And here's some of the source files in R. And we'll look at these, and then we'll see. We'll see how it goes. First of all, whoa, before we do that, what haven't we seen? We haven't seen any Fortran. So let's make that happen first. Let's make sure that we at least pull it up so we're not losing track of it. I'm guessing that we'll just look for all F stuff. Huh. What's the Fortran file extension? F90, F95, F03. You would think I would find it with that find command. Where else would it be? PO share doc. You have Fortran.R. Is this in Fortran? This looks for possibly Fortran-y. Okay, so why didn't I find this? Did I do? Okay, so okay, so I was doing something wrong. All right, so there's a few Fortran files here. BS Boulevard, Pulved, LOS, PPR, QS Bart, SGram. I don't know what those are. This is XXX file, probably grown-ups only, and some other stuff. So I don't know. Let's go back to R, the R functions, and then we'll come to the Fortran later. All right, here's apply. Apply should work like apply does in other functional languages. So apply pandas. So data frame apply in pandas is we're going to apply a function along an axis of the data frame. So apply, you give it a function. It's kind of like a map, and then you give it an axis. I think it's more or less the same thing in R. Returns a vector or array or a list of values obtained by applying a function to margins of an array or matrix. So you can maybe do apply one. No, the matrix goes first, right? So df1 max, and then df2 max, like that. Okay. And it's fast. R is a nice and fast language. Okay, so apply is going to, it's going to look at your fun. We're going to call match.fun. This is, I guess, probably doing some sort of lookup in a function table of things it knows about at runtime. And if you passed it simplify, we'll set the variable simplify. We're going to ensure that it has that X is array-like by checking that it has a valid dimension, I guess. The dimension should be kind of like shape in what? Pandas? Okay, so dimension is 5.2, and then we'll get the length of that, which should be 2. And I accidentally added an 8 there. Okay, yeah. All right, and so if we don't have a length, then we stop because it's not the right kind of object. But we're not. This is kind of like duck typing because we're not actually doing a type check. We're just checking that it has something that dimension can understand. But if we do have a length and we check it if it's an object, if it is an object, we check if the length of the dimension is equal to 2L. Where L came from, I don't know. L must be long. Okay, so if the dimension is 2, then we know that it is a 2x2 object as opposed to like an array. So we cast it as a matrix. Otherwise, we cast it as an array. And now a chord dim as coercion can change it. So we get the dimension again. We get the names of the dimensions. We set ds to the sequence length, which I don't know how that's defined, but if we do dim names of df, we should get the column names. Okay, so we get the index. We get both the index as it would be called in pandas, which is the names of the rows, and also the names of the columns. And then what is sequence length? Is it defined on a matrix? How about points? Okay. So seek generates regular sequences, and then seek length is, I guess, generates this. It's like range in Python. To toggle around with the code. What do you mean by that? Do you mean like running this code in particular? All right, and now we extract the margins. Where is margin? Okay, so margin is the thing you passed in. It's like 0. If you want row, I guess. And no. How does it work? So when I give it, yeah, so 2 is across columns and 1 is across rows. What does min do? Yeah, okay. So if it's a character as opposed to a number, then that's, I guess it's going to assume that I'm asking it to look at a specific column. How about points? X must have named dimensions. So if I look at names of df. Oh, okay. So these are the names of columns. I guess the dimensions themselves can have names. I don't know how that works. Okay, so it might have named dimensions, in which case you can ask for the margin by name. Otherwise, we call d at negative margin. That's d call. And then we get D at margin, that's D ants. So D at df at -1 is everything but the first. And then that's everything that's just the first column. And similarly, I would guess for 2. Okay. And then, what is dn and ds? Okay, so we get these things. We do another check. Then ds is just the sequence, like 1 to whatever. dn is the name of the dimensions. And then we get the call and the answers for those. And then we're going to do the calls. So we'll get the, we're going to take the product of the answers. I assume this is call and answer. I'm not sure how else to think about those variable names. Then we get D2, we check if it's 0. Then array with 0 extents, return empty result, blah, 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 blah. If we're down here, it's not 0. Then whatever A perm is, we're going to pass it the concatenation of S call and S answer. And we get a new X. We look at, we set its dimension. This is like coercing it to a specific shape by taking the product of the calls and whatever D2 was. We get the answer, I guess, by taking D2 and calling vector with the string list on it. I don't know what that does, but we can try it on points. Oh. Does that make a null list? Make some sort of a vector, I guess, of a certain size. Then we look at the length of the decall stuff, check if it's less than 2, and do some stuff. I don't know what force call is, etc., etc. Then we get answer dims and dim names. The answer list, the answer, I guess, has a thing called list. And or maybe like whether it's a list depends on whether we're simplifying and if something is recursive. The answer at the first, I guess, like inner dimension. And we set the length of the answer. And we get the names and so on. Okay, so somehow this is doing apply, but I'm not sure exactly how to think about all of this call and answer stuff. All right, so that's apply. And I thought there was something that I wanted to see real quick in the middle here, but I'm not sure that I remember what it was. All right, so let's take a look at some other stuff. So array should be, I would think just like a one-dimensional matrix. And so array is a function. You give us some data and a dimension and some dimension names. So if I do array of points, I think that's just the same as points. If I do some sequence, I can give it a name like dim names. It has to be a list. I don't know how to make a list. Maybe I just like concatenate it with nothing. Maybe a list has brackets. Don't really remember. I'm not sure. List. Okay, there we go. That's some array. Okay, and it wants the number of It's the same number of names as the sequence length. All right, great. So that's what the array function does. We check if data is atomic. I have no idea what that means. We check if it's an object. And we may return internal array data dim names. So internal might be calling out to C. Otherwise, I guess we course it as a vector. Again, we check if it's an object. Then we get the dimensions as an integer. And maybe fail out. We take the product of the dimensions. I guess probably because we're flattening it, and then we're going to unflatten it, and so on. We have the slice index. I think this is, I guess, probably like you can think of this as an implementation of the notation to index into something. Is R something I shouldn't override? Okay. So R is going to be this array, and then I can index into it. And I think that's maybe what this is implementing. Margin is maybe so that I can do multi-dimensional stuff. In this case, we have a one-dimensional array. And we check if margin is a character. So I do have a... Yeah, I'm not sure how that works. This is some function to provide dim names. A split, the array split part used by apply. Okay, so this is like an implementation of the thing that apply needs. I don't know. We looked at apply already. Maybe I can open it back up. There might be a call to a split here. No. But somehow I think that this is implementing something that apply relies on. There may be like a syntactic way to access it. And array 2df. So I made my array. R is has some length. Let's make a new R that's an even number of entries. And do I get to set the dimensions? Dim. Oh, the dimension is the length of the data. So I guess I can't make, can I? So what if I take sequence 4, or yeah, sequence 3 and sequence 3 and concatenate them? That should be a long sequence. What if I take, how do I make a two-dimensional array? Maybe it has to be a matrix. Multi-dimensional array in R. So I have two vectors. And I can concatenate them. And I can pass it the dimension as a thing. So I can try, this is 4. Well, 12. I can try the dimensions is and now I have a 4x3 matrix. And so that's an array. I don't know, I guess we could call it is matrix on it. I don't know if my original one was a matrix. Like a degenerate matrix. Okay, so a one-dimensional thing is not a matrix. Fine. Fair enough. Okay, so that's kind of how, I'm just trying to get a sense for how it thinks about some of this stuff. And so these I think is kind of like implementing standard utilities for accessing the array in a standard way. Here's assign. This should be assignment. Assign is a function that takes an x and a value, a position which is set to -1, an environment, which is we're going to call as.environment on the pos, whether it inherits, whether it's immediate as opposed to lazy. And we call it the internal assign with the same arguments. Yeah, I don't know. I'm not sure I know how to do this. I mean, like I could try. I don't even know if I can paste this function, and I could try executing it on the I don't know what happens if I override assign. Let's override assign to take the negative value. And then we'll do f is equal to 4. It doesn't seem to set it to -4. All right, so I don't know. It doesn't seem like it can do that, but maybe that's because assign is being called kind of somehow differently. Like I'm redefining assign in my local area, but under the hood, it's calling like an already compiled assign function. Backsolve. This should be some sort of backpropagating solver, I would think. So backsolve is a function that takes a 1, or rather an L, an X, a number of columns, whether it's upper triangular, and whether to transpose. And then we're calling internal backsolve. Except that was forward solve. So where's the internal backsolve? So a bunch of these functions, I'm going to guess these are in the C code. Backsolve. So here's backsolve RD. That's, I guess, the documentation. Here's the S expression. This is looking Lispy. This is, I think, just saying that, okay. Yeah, so I think that maybe what this is saying is a couple of things. Do backsolve is a function. It returns a thing, and it takes as arguments 1, 2, 3, 4 things. And although it's not an especially informative type, the type of things it takes are S expressions. In fact, you should expect that almost everything takes an S expression. An S expression in this way of thinking, kind of probably similar to pandas, is an S expression is the thing that is like a generalized array or vector or matrix. And I think that's what's up. So this was written at a time when Lisp kind of was the way that people were thinking about doing not only AI, but also things like mathematical software. So like Maxima is like a pre-Mathematica 1968 to 1982 math software that should do things like symbolic integration and differentiation. Let's see if we can find Maxima integral. And things like polynomials. The Maxima system. All right, look at that. Look at that font. This is somebody literally either hand typing on typewriter or whatever those printers are called that have those like IBM ball cartridges. But you should be able to do things like integrals. Look at this math. Can you imagine if you had to read monographs like this? And whenever this was, the 70s or 80s? I think this is Maxima. Yeah, okay. So you can, it understands things like log x squared plus x plus 1. And I believe it understood that by using Lisp. In fact, let's double check that before I say that and I'm wrong. The Project Max symbolic manipulator is one of the oldest general purpose computer algebra systems still in wide use. What? Really? It was licensed to Symbolics, which I think is a Lisp machine company, unless it's also the name of other things. Symbolics. a privately held American computer manufacturer that acquired the assets of the former company and blah, 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 to maintain the open genera, as opposed to general, Lisp, and the Maxima computer algebra system. Okay. So I would like to see a table that tells me in no uncertain terms that it was implemented in Lisp. But this looks like some stuff about Lisp compilers, Lisp machines. Yeah, it's Lispy. I don't know if everything is Lisp, but something is heavily lisped up. And then we also have the fork or maybe reimplementation Maxima, which should also be Lisp. In a just world, it will be Lisp. That's here on SourceForge, and it's written in Common Lisp. Okay, so I feel redeemed in my going out on a limb. So that's why we see so many expressions. That's the environment this was growing up in, and it seems to work. It produces a nice language. Backsolve is in C, and I guess that the C code has this like do underscore prefix to the Lispy function. So whatever the code that kind of like assembles R is going to, I guess, strip this prefix, find the corresponding Lisp macro or whatever. And here in C, we at least get the names of variables. So the first sexp is a call, the second sexp is an op, and so on. And then it's going to return an attribute hidden, sexp. I don't know what attribute hidden is doing. Is that a general C thing? I don't know if that's a general C thing or if it's part of this repo. Okay. Unless I misspelled it. Did I misspell it? Let's try one more time. Whoop. Something's really wrong with copying and pasting on this machine. I don't know what it is. I think it's either GNOME or Ubuntu specific. Okay. Cool. All right. So, and then we're going to, whatever it, nprot. Prot, I'm not sure. Prototype? I don't know. But we're going to, R is, we're going to car and cdr our way to success here. So, car, I think, is head. I might get murdered by the Lisp Mafia if I get this wrong, but I think car is head. And then cdr is tail. Although, yeah, so R is set to the head, I think, and then the rest. So args is reset to the rest of args because we've consumed one thing, and so on down the line. We'll set NNR to the number of rows, and NRB to the number of rows of B, and so on. And then we're going to do some sort of algorithm. This kind of looks like all conversion. We're going to check for zeros on the diagonal. We're going to protect. We're going to allocate some stuff with this protect call, whatever the protect is doing. And we're going to copy some stuff. And then we're going to call Fortran 77, DTRSM. Passing in some stuff like L is upper, question mark. U, no. L is the first argument. Upper question mark U. It means what? I don't know. We have L again. I don't know what any of the syntax is. Real, I guess, is probably saying this is a real number. Whatever F cone is. We've got 4 F cones in a row. And then we can probably just look up this DTRSM. Fortran. Sim. TRSM. TRSM solves one of the matrix equations. Op A x equals alpha B, or x op A equals alpha B, where alpha is a scalar X and B are M by N matrices. A is a unit or non-unit upper or lower triangular matrix. And op A is one of the identity function or A transposed or A times H, which I'm guessing is maybe, since they wrote the transpose just next to the matrix, I'm guessing H is maybe just the Hermitian conjugate. So that's TRSM. Why would you name it TRSM? I have no idea. But DTSRM is what? Distributed? Here's a subroutine. I don't know. All right, here we go. It solves one of the matrix equations, op A x equals alpha b. And we saw stuff like this in Python. I think it was in, I want to say PyTorch. Everyone's always, first of all, everyone's copying Fortran and R and all the Lisp stuff. We get it kind of all in a nice package with stuff like Python. But it's good to know that all of this stuff has like roots. Okay. I don't know what the difference is here, except we have the identity operation or A star star transpose. And X is overwritten on B. So we're reusing the memory. I don't know. I thought AT was transpose. I don't know what A star star T is. Star star is often the notation for taking a power. So that seems like it would be A to the T, which is the notation for transpose. So I don't know. I'll ask the AIs. In Fortran, how do TRSM and DTRSM differ? Okay, so this is I guess this stuff comes from BLAS, which would make sense. That's the specific Fortran thing that they're using, I think. And DTRSM is a specific implementation for double precision. Okay, so D is double. Okay. So I'm going to ask it about why. So why does TRSM say this thing about op? This was a failed search, so I can get rid of that. And where's the, yeah. But DTRSM says, so it's confirming that AT is supposed to be A to the transpose. AH is the Hermitian, the conjugate transpose. And DTRSM, blah, blah, is double precision real matrices. Okay, so it has to be real numbers. The conjugate is the transpose. The Hermitian conjugate is equivalent to the regular transpose. I'll say, but why the star star T versus the A star star T versus AT notation? So AT refers to the transpose. Oh, okay. I'm not sure if I believe that that's why the stars are there, but that's fine. So what does TRSM stand for? Maybe it's like the arguments? Transpose? No? Okay. And I'm pretty sure BLAS is often, oops, I misspelled it. But I'm pretty sure BLAS is has one of the implementations is in Fortran. Basic linear algebra subprograms. All right. There are the de facto standard low-level routines for linear. They are for linear algebra and have bindings for both CBLAS and Fortran, which is just says BLAS interface. Ah, ChatGPT is not going to tell me. Are you? I'm going to ask it in like a really shouty voice. Triangular solve matrix. Okay, great. Okay, so that's some Fortran stuff. And let's verify that car and coulter do what I think. So car of cons xy. Cons xy is the list consisting of xy, and that must be yc. Yeah, okay. So the reason that why this is concatenate is that it's an abbreviation for cons, I bet. In R? Combine. Yeah, right. You say it's combine. I'm on to you. Okay, so car of cons xy should be x, yeah? And coulter of cons xy should be y. So that means tail, right? For this reason, the operations are sometimes given the names first and rest, or head and tail. Cool. All right, so I didn't realize R was so lispy, but that might be one of the reasons I like it. Or it might be one of the reasons I like Lisp, because R, I think, was the first language that I programmed in, and I felt like, this is cool. This is fun to work in, as opposed to other things, which felt like you could get things done, but it didn't seem optimized for me. Here's data frame. This is going to be an implementation of, I guess, like similar to the pandas data frame, we're going to have an underlying object, which is this kind of like generalized matrix. I think a tensor would be how the machine learning people call it. I forget exactly if they're the same concept, but we're going to also have things like row names, and it's going to be like not just the matrix itself, which is just a memory regions full of floats or integers, but the data frame is going to have metadata to capture the idea of like you're working with a specific data set, with whether it's medical data or economic data or whatever. Okay, so I worked in college. I worked in like psychology, and we used it for like psychometrics, like developing tests, analyzing tests, and it's just fun to explore data in. Before that, like a lot of psychologists use like GUI driven applications. At the time, I don't know if they've moved on, but things like SPSS, where you're kind of given like a general an Excel like whatchamacallit, UI, and then like to do analyses, you like grab something up here or something, maybe analyze, and then ANOVA or something, and you like pull which variables do you want? I want gender and education. And I like spent a bunch of hours doing that, because that's what Like that's what the gig was at the time. And then when I found R, I was like, wow, this is just vastly simpler and vastly more powerful. So I think that was part of it. But it's like a very fast functional programming language that really only does statistics. So you get feedback very quickly, and you can kind of like hammer things out and explore things very quickly. Even with something like pandas, it's just a little bit slower. It takes longer to like render a graph. They're just like little pain points that you probably won't even notice if that's kind of like all you've done, but just R just feels a lot snappier to me. Okay. And I think that since this is, I think, mainly going to be about things like names and metadata, it may not be so important. I'm seeing a bunch of name stuff, row names, column names. Is it a data frame? Print. T.data frame is probably, I think T is transpose. Yeah. You can get dimensions and all that sort of stuff. So these are like, in an object-oriented language, these would be like you implement class data frame, and you would have like a function like as or like convert to. Or rather, you would probably implement that in any class that can be convertible to data frame. But this is a more functional approach where you somehow, when you call as data frame on something, it's going to find the appropriate function. Or rather, maybe there is just one, as opposed to something like Haskell, where like you have something like 2JSON and you have to implement a converter each time. Okay, and you can convert it to a matrix and so on and so forth. Okay, so that's data frame. That's fine, we'll move on. Vector. Vector is going to be similar to the other stuff. And in fact, I don't think we need to look at it. Optimize.c. I'm going to guess it's mainly going to call Fortran. Was it F77? No, maybe not. Optimize. So fmin, I guess we're always minimizing. Approximation, x to the point where f attains a minimum on the interval ax bx is determined. The method used is a combination of golden section search and successive parabolic interpolation. Convergence is never much slower than that for a Fibonacci search. I don't think I know these terms. So let's look them up. Golden section search, successive, parabolic interpolation. That's maybe, I don't know what kind of parabolas we're interpolating with. And Fibonacci search. So golden section search is a technique for finding an extremum of a function inside a specified interval. Okay. I'll look at that later. And similarly for all of these. Okay, so the parabolas are just polynomials of degree 2. This is maybe just some sort of polynomial interpolation. And it's related to Simpson's rule. Which it seems like, how could it not be? That was my initial thought, but we're not doing integration. I think we're just doing, in general, like something like root finding or minimum finding. And here's the main loop. We're gonna, whatever A and B are, those are probably things we, maybe the interval endpoints, we're gonna maybe start in the middle. We're gonna take the something absolute value, float absolute value of x. I don't know what L3 is, and epsilon is probably some small number. Maybe tolerance. We'll check stopping criteria, fit a parabola, and then check some more stuff. So this is like the implementation of parabolic interpolation. And it's in just C. So let's see if we can find an example of how to call optimize. We haven't seen yet how to define like a general function. Like surely there's a sine function. But how do I define like a polynomial? Like here. So f is going to be this function. I guess you have to tell it, you have this function keyword. You're going to tell it what the arguments are. And this is a the polynomial you get by subtracting a from x and squaring. And so let's actually have it take a single function. And we'll have it look for 1.5. And so you could do that. And then we should be able to just call optimize. Presumably the interval is the second thing. And the minimum is 1.5. And it happens at 0. Right? 1.26 times e to the negative 29. Okay. So that's optimized. Here's the stats header. We have a bunch of F77 stuff. A starting point to extract such prototypes for .fortran calls is gfortran -c. So this is some call to the Fortran, I guess GNU compiler is probably what G stands for. And this is some Fortran stuff. L-minful, KMNS, and I'm guessing these are also blast routines. KMNS, and what is it? L-min-fl. The first one is the first result is the R function. lm inful checks and analyzes leave one out p-values and a variety of influence measures in linear regression. Okay, so this is some function used in linear regression. And what about this KMNS function? What about BLAST? K-means? It's probably K-means. And whatever these are. So this is like hooking up some, I guess, H cluster. H cluster is probably some clustering code. So these are, I guess, statistical functions that are sufficiently important that they wanted them to be super fast and implemented them in Fortran, I think is probably what's going on. This should be some Wishart distribution. I don't know why it's in its own. It was like one of the only distributions in this source stats source C files. Simulate the Cholesky factor of a standardized Wishart variate with dimension p and new degrees of freedom. Yeah, I don't know why this is in C. So there's a Cholesky factorization and then the random matrix stuff. Let's look at the Wishart distribution. Maybe it involves special functions or something. So I guess it's used in random matrix theory, which we'll learn about, but it involves the inverse gamma function. That might be the source of why they don't want to do it in pure R. Rather, not the inverse gamma function, the multivariate gamma function. So I guess, yeah, they have to integrate. They have to numerically integrate, and it's mainly an exponential, which shouldn't be too slow, but is there like an integration? There's integer is matrix. This is some stuff about RNG state. We have an F77 call here, DOP OTRF. This is presumably just another LAPACK or BLAST call. Okay, it's a Cholesky factorization. I guess that's probably the reason they want it in C. Maybe. We also have the standard Wishart factor and another F77 call. So where's standard Wishart factor? Oh, that's the function that we are in now. Is it? No. It's just a function defined in the same thing. Okay. This is norm rand. Yeah. I'm not sure. I think somewhere in here there's probably some integrating going on that might be either implicit or hidden somewhere in Fortran or something, or in another C call. Here's Callman. We have Callman-like, a bare-bone versions of this struct TS. This is an R. Callman run, Callman forecast. We've got this dot call, C Callman-like. I'm guessing that's the C implementation. So it seems like we could call C functions no problem. I'm not sure if I saw where Callman-like was. Maybe it's here? Nope. That's the R version. Here's the thing, just defining it as a Lispy thing. And stats ARIMA, which is like an autoregressive like finance model, isn't it? Almost no checking here. Uh-oh. Okay. So whatever this is, Callman-like, it's doing something Callman-y. But what? I don't know. I don't know what it means to be like. I don't know what it means to be Callman-like. And it doesn't really seem to say. But we'll look up Kalman filter. Kalman? Also known as linear quadratic estimation. We have some prior state of knowledge. Whatever this notation is, I guess we're conditioning on k minus 1. We have a prediction step based on a physical model, and an update step. So it's some recursive, I think it's like a control theory type thing. But I don't really remember, so we'll look that up. And what was the other thing we were going to look up? Oh, I wanted to verify that what's going on with ARIMA. ARIMA. Autoregressive integrated moving average. Okay, so it's a moving average, it's integrated somehow, and it's autoregressive. Let's see. Here's the mathematical formulation. Given time series data xt, where t is an integer, an integer index, and the xt are real numbers, an ARMA p prime q model is given by xt minus alpha 1 of xt minus 1 to the difference. Oh no, this whole thing is a one formula. So we're subtracting off a bunch of stuff. I guess each time step previous. So p prime is a parameter that I guess tells you like the length of the thing we're estimating or predicting. And we have p prime minus 1 alphas. And we're going to set them to be equal to epsilon t, which is presumably like Gaussian noise. Plus, we've got q thetas. And we've got a bunch of epsilons. But these are like the older epsilons. Just like these are the older x's. And equivalently by 1 minus the sum from I equals 1 to p prime of alpha I L to the upper I, which is L to the upper I is the lag operator, whatever that is. That's the thing, I guess, that gives you the older versions. Oh, okay, so I guess thinking of this as something in memory, the lag operator is going to like go back and visit the appropriate cell. And then epsilon I. And I hope these are epsilon I are errors. The error terms epsilon t are generally assumed to be independent, identically distributed variables sampled from a normal distribution with zero mean. Okay, so that was good. That's what that notation normally means. The alpha sub I are parameters of the autoregressive part of the model, and the theta I are the parameters of the moving average part. And so I guess once you've put it in this form, you can, I guess, think of this as a polynomial. It has a unit root. And so you get to do some like factorization. And ARIMA PDQ process expresses the polynomial factorization process property with p equals p prime minus d, and it's given by this. I guess this is a modification of the model we just looked at. Maybe this is No. I guess this is just a generalization where we have another variable or something. At any rate, this seems pretty much the same. Whoops. Except we've got a 1 minus L to the D factor now. All right, I'll look at that later. Okay, so this some ARIMA stuff. I'm pretty sure it's used in finance, but I didn't actually grep for that. But autoregressive models in general are common in finance. Here's Tukey HSD. Multiple comparisons for R. HSD, I don't know. But we've got this use method Tukey HSD, Tukey HSD.AOV. I don't know what AOV stands for, but it's a function which takes an X and which, like maybe which comparisons to do or which like row or column to look at and what confidence level you want. We're going to get model.tables. Where did model come from? I'm not sure. Asking for the means. What if I do? So this does seem to be a function I have access to. Compute summary table for model fits. Okay, so if I take a, do I still have, let's set M to be the linear model of, what was it, points by assists, let's say. Points by rebounds, I think. Just randomly choosing things. And I can maybe do model.table of M. What was it, tables? All right, fine. Now I need to know. Is AOV ANOVA? Analysis of variance? Fit and analysis of variance model. Okay. So can we do, I don't know what the syntax here is, but let's try taking this linear model and making it an ANOVA. And now at least the function, we get the grand mean and some rebounds and stuff. And I could probably take I can make the model include more stuff. Okay, great. So that's what model.tables does, and we're using it in the Tukey. I don't know what HSD is. Tukey. Honestly, significant difference. Okay. I meant to do Wikipedia, but this should be fine. I'm not sure it is fine. The font was unreadable. Here. The Tukey's range test. The method was initially developed and introduced by John Tukey for use in ANOVA. Cool. And it's first, like what? Something about comparisons, single step, multiple comparisons. Okay. So you want to do multiple comparisons in a single step if you can. And Tukey has a way to do that. That keeps you honest. One of the reasons it's important to be kept honest when it comes to multiple comparisons is that you can use them to like search for things. And the more comparisons you do, the more likely you'll eventually find something just by coincidence. So you want to limit you don't want to cast too wide of a net. Bandwidth, I'm going to guess, is related to kind of like Bell Lab style bandwidth stuff, like old control theory stuff, maybe. Empirical timing. I don't know what this is. UCV, bandwidth UCV. Let's look that up. UCV versus BCV. Bandwidth selection. Biased cross-validation versus some other cross-validation, unbiased. Yeah. Okay. I think I'm going to kind of like plow along here. Birthday. I'm just guessing this is the birthday paradox. Q birthday. P birthday. Like quantiles. And you give it a probability. Computes answers to the generalized birthday paradox problem. P birthday computes the probability of a coincidence, and Q birthday computes the smallest number of observations needed to have at least a specified probability of coincidence. So P birthday, I don't know what classes is. Oh, classes is like how many, in the case of the standard birthday paradox, class is like the number of days of the year. And so this is the, so this is the standard birthday paradox. I think coincidence means like, coincidence is like how many, coincident equals 2 is saying you're looking for 2 people with the same birthday in a year that has 365 days. So if I have a class of 1, probability is 0. If I have a class of 4, probability is 0.016. A class of 10 is kind of increasing, but a class of 50 should be over 90%. So if I plot this, I don't know if I can do this. I think I can do this. So let's take the function that's given by kind of currying the birthday paradox. And we can plot it. How do I do this? Our plot function. Do I have to give it an explicit range of x? Plot x, y. Plot table. So here's a function. X is the square root of our norm. This is okay. So what if I do x is equal to sequence from up to 100? I think I can just do this. No? I don't know. I did something wrong. I'm not going to fix it now. But something along those lines is how you do plots, I think. All right, but anyway, that's the birthday. Here's integrate. This is, I'm going to guess, numerical integration. Integrate function f lower upper. Yeah. So maybe if I use an existing function. What if I just plot sine? I just plot sine? I can do that. Can I just plot b-day? I think there's something wrong with my b-day function. Is it because I used braces? I don't know. Yeah, whatever. But we could plot, you can integrate sine, I think. And I think I have to give it limits of integration. Let's integrate it from -1 to 1. 0 with some absolute error. What about -100 to 1? Then we get 0.322 with some absolute error, which is close to 0. Okay, this is Mahalanobus distance, I assume. The save speed in customer use case. It's a function. You have x, center, cov. I don't know what this is, but we're going to move on. I think we're just going to kind of plow through these quickly. So here's plotting for the linear model. You give it some x, which is supposed to be some sort of linear model object, in which is a concatenation of 1, 2, 3, 4, 5. I guess this is maybe which plots to show. You get captions. These are probably 1, 2, 3, 4, 5 captions. So residuals versus fitted, QQ, residual, scale location, etc. And then whatever this Cook's distance thing is, some like string label, I guess. And drop inf. I guess this is like dropping in infinite things that are infinite, I suppose. And to the type checking here is we're calling this inherits function. And I don't know what that does, but we're checking if it inherits LM and so on. And then we're just going to do the different plots. This is just like a script to run through a bunch of different plots. And somehow they're going to check if you like press enter or whatever on the command line, it'll advance to the next plot. Optim, I'm just going to ignore. Power. This is for like power of a t-test. This is just some formula that they're implementing. But I think we now have a sense of how a lot of this stuff is implemented. This predict function just seems to be calling out to whatever use method predict is. I'm going to guess that there's a C function corresponding to it. I'll ignore QQ plot, SD. I don't know how. Okay, so they're always computing it it's the square root of the variance, which is always true. I don't know how they're computing var, but it's a standard formula. Here's a t-test. Not only, so this is the test, so it's going to have to figure out what the like critical value is. It's going to have to look up the appropriate t-test table, which it will do by TT. What is it? So we have things like Q norm. What's Q norm? I think it should be a T norm. T norm? There should be some model of the t-test. The t distribution, statistical distribution, is what I'm trying to say. And we're going to use the various standard distribution functions to get it. So norm, p norm should be the PDF of the PT, I guess, is the PDF of the t distribution. Density distribution function, quantile function, and random generation for the t distribution. This is what I was trying to say. So dt is, I guess, the density, pt is the distribution, qt is quantiles, and rt should be what? Random generation. Okay. Yeah. So I wasn't sure what those classes of functions are called, but they implement them for every distribution. And I don't know where they're implemented, possibly in C. Let's just look for the normal distribution. Yeah, we have rmath.h0.in that has just the signature for the functions, uniform distribution, normal, gamma, beta, chi-squared, non-central chi-squared, and so on. Here's qnorm. That's, I guess, what's in nmath, numerical math, and this is, I think that's the floating point definition, right? IEEE 754 for standard for floating point arithmetic. So we're just checking if it's a valid floating point number, if it's NaN, etc. And this is something about the boundaries being negative infinity and positive infinity, I guess, for the normal distribution. We check if sigma is less than 0, and so on. And then we call r dt q iv. And I'm not sure what that is, but we get p underscore from that, and then we get q from p underscore by subtracting 0.5. And then this might be the root algorithm. This looks pretty gnarly with these long numbers that have high precision in the way they've written them down. And I'm guessing that this is just what the algorithm is. And there's really no sense of trying to figure out what these are doing. But it seems to be citing a paper, Wikura, page, or rather a book, 478, Minimax Rational Approximation. R32 is for t between 5 and 27, and so on. Cool. And that's, I think, enough R for me. It was laid out pretty much the way that I expected it would be. I'm not going to look at modules. I'm not going to look at apples. And I'm not going to look at any more at nmath, although that's probably a cool folder. Yeah, so a lot of it is written in the R kind of like scripting language, which makes sense for things that don't involve a lot of the overhead. And then they jump to C as needed. And then the linear algebra is implemented largely in Fortran. And it's very Lispy. It's much more Lispy than I realized. And it kind of, and going through that kind of reminded me of some of the functions that I had long forgotten. And it's fun to use, so you should check it out. So that's all for now. Thanks for watching.